By now you've probably figured out that these fill-in-the-blank notes are simply trying to hit the highlights from each section of information that's been photocopied for you. So we're pulling out the things that you're really responsible for. We have something called the Hertzsprung-Russell diagram, and it looks something like this. And what it really is, it's a snapshot of stars. Up the left, it talks about solar luminosity, the brightness, and across the right, it plots the temperature. Strangely, though, the temperature is going from bigger to lower. So you see that things that are red are lower energy than things that are blue over on the left. Of interest to us, well, a lot of these things in bold might be interest to us, the red giants and white dwarfs, but also our sun is of interest, and our sun is a yellow star. We're really not going to use this chart that much. So a star's mass determines a lot of its characteristics. Its brightness, its color, a lot of that's dictated by its size, and its lifespan. How long is it going to be around? What we're looking at from red giant on the rest of the way in the notes here is what happens to stars of different masses once they burned up all their fuel. So if we look at our yellow star, it's going to become a red giant and then eventually potentially a white dwarf. What does this mean? Well, we know our sun is roughly 5 billion years old, which is halfway through its 10 billion years of age that we expect. And it will start to change when it runs out of its hydrogen, no longer being able to fuse hydrogen into helium. We know that stars are a balancing act between the energy they throw out from the fusion that wants to make them bigger, and their own mass and gravity wants to make them smaller. And those two forces have to balance. So after 10 billion years, less heat's going to be produced, so we'll have less outward force, and all that mass is going to start to contract, and that means collapse it towards the middle. As it does this, it's going to generate enormous heat from things like friction, and this can restart the fusion. So now all of a sudden you restart the fusion, and it's going to suddenly expand and form a red giant. Now when anything expands, it tends to cool, and as it forms this red giant, it does say here in the notes it's going to engulf Mercury and Venus and perhaps Earth. So you can see it's going to get a lot bigger. Now down here it says a star with a initial mass of up to 10 solar masses will form a white dwarf. Now the solar mass comparison just means we take a mass of a star and we divide it by the mass of the sun. So in other words, something with 10 solar masses, that is 10 times more massive than our sun. 50 solar mass would be 50 times the mass of our sun. So now we look at things like supernovas, neutron stars, and black holes. The supernova, well, nova means new, and so it's a very ironic name since we have this exploding star at the end of its lifespan. And it says that stars over 10 solar masses have enough mass that when they fusion, they can fusion carbon to heavier elements. Our star is just doing hydrogen and helium on the periodic table, very small elements. But carbon, also we got a mass of 12, and we're getting up to bigger masses because it talks about things like iron and nickel and whatnot there. So we look at this. If we have enough mass, 10 solar masses, when it collapses, you get this incredible collapse, generates all this heat, and you get this massive explosion. And this is what many astronomers spend their time looking for. They look for supernovas, and they'll have to look through all kinds of data that they are receiving from telescopes around the planet. When we go to a neutron star, now we're talking between 10 to 50 solar masses. That's enough mass that when it collapses, it becomes insanely dense. And so it's going to be so much mass packed into such a small volume. Well, what does the neutron part mean of a neutron star? What this is saying is you're taking atoms, and atoms we know are protons and electrons. And if you squash a proton and electron together, the result is a neutron. So all kinds of mass packed into a tiny, tiny volume. A pulsar is a type of neutron star, but it's one that rotates. And as it rotates, it sends out radio waves. And so essentially it's like if you're looking at a lighthouse. It looks like just every so often a pulse of radio waves is going to come your way. Black holes. Now we're talking about over 50 solar masses that when it collapses, it may supernova. Talks about making heavy elements. That would be from fusion. And if we still have at least 4 solar masses left after the supernova, then it can become a black hole, where we have so much mass, so much gravity, that it will not even let light escape. And in fact, the escape velocity for trying to get out of a black hole is the speed of light, so we recommend you not try it. So if we look at this, we're talking about a black hole with 10 solar masses. All of a sudden it has a diameter of just 60 kilometers, roughly from here to Chilliwack. So one of the problems is they do not give off light, and that makes them difficult to detect. So if you're a black hole hunter, then you're not going to see a black hole, no light given off, but you'd be looking for things being affected by a black hole. So you might be looking for an area where material is being moved towards something that is black in this case. So that's our first look at stars, but in the upcoming videos you'll see more and more detail filled in and descriptions of these different types of stars, so pay attention.